Okay, so let's start. I'm recording this for other folks that wouldn't be able to join. We have here David Bowler, and to introduce us the Conquest application. David, go ahead. You can start.
Okay, that's great. Let me share my screen, and we'll start. Okay, hopefully that's the right screen. So my name's David Bowler, and Ophir's asked me to give you a bit of an introduction into who I am and what the Conquest code is. And fundamentally, Conquest uses quantum mechanics to calculate material properties. So I'm based at University College London, UCL. You can see down here, you've got the old part of UCL, which dates back to about 1830. But I'm actually based in this building down on the bottom right, which is the London Centre for Nanotechnology, which is actually only about 20 years old. So I'm a professor of physics at UCL. My research is basically in the field of condensed matter. Mainly I do simulations using atoms or atomistic simulations. And I've generally been very interested in semiconductors. This includes silicon, it includes complex oxides such as strontium titanate and bismuth manganate. And I work very much in the field of computational physics. This is a vital tool for the interpretation and prediction of results, and it bridges between experiment and theory. The area I work in is known as an ab initio, which is an approach which technically requires no data beyond the positions and the elements of the atoms you're interested in, though it's a little more complicated than that. There are, of course, various approximations that are involved. And the standard approach in that field is called density functional theory, or DFT, which is what Conquest is based on. I'll explain this very briefly in passing slightly later on. So Conquest itself is developed mainly in three centres. It's developed here in the UK at UCL. It's developed in France, the Université de Bordeaux. And it's developed in Japan in the city of Tsukuba at the National Institute for Materials Science. And it's been an international collaboration for at least 20 years. We've worked together across those three sites now for 10 years, and the international collaboration is vital to its success. So just to give you a little bit of background, so I guess that there are people from all sorts of different areas. So computational physics is very much trying to interpret and predict experiment and theory. So experiments can extract certain amounts of information from the world around us. Theory can predict certain things, but the two aren't always compatible. Experiment is often messy and difficult, and theory is often pristine and rather limited. So by doing computing, we can actually bridge between those two and calculate things that can't be measured, and also measure things and predict things that we can't do with theory. And you find it in all sorts of areas. So in particle physics, in quantum chromodynamics, in material science, using electronic structure and atomistic modeling, coarse graining, finite elements, that's very famous within supercomputing, fluid dynamics, climate science, planetary dynamics, galactic dynamics. So we can work on all sorts of different length scales. And the area I work in is fundamentally what's called materials modeling. And materials modeling itself actually spans 3 or 4 disciplines and many orders of magnitude in terms of length scale. So at the very smallest length scales, down at the nanometers or below, we involve physics. You can bring in chemistry as you go up towards the atomistic level, and then you start to move into the areas of material science and engineering as you get larger. Of course, you can't use atomic atomistic modeling beyond a certain level. Once you get past about 1 billion atoms, then really atomistic modeling becomes unfeasible, and so we shift to microstructure and macroscale modeling and this kind of thing. But I'm going to concentrate today in terms of what we do on this area of atomistic simulations. So in this case, what we have is we have to specify a portion of the universe that we're interested in, which tends to be called a simulation cell. So that's a box. It can be cubic, it can be orthorhombic, so right angles but different lengths, or it can be of any sort of size and shape. And typically you'll have anywhere from 2 atoms in that box to 2 billion atoms. And the fundamental intention, the fundamental aim, the operation that we have to do is we start with the positions and the identities of the atoms, and from them we calculate the energy. And from the energy, everything opens up. Now, I should just point out that the box here is a representation of the universe or the thing that we're studying. So in the case of physics, the kind of material science problems we're using, that box will be repeated infinitely through space. So we're using what are known as periodic boundary conditions. And the practical aspect of this is that if an atom leaves one side of the box, so for instance, this atom that I'm circling here is actually an image of this atom here, which is also an image of this atom here. So the box is repeated periodically. If an atom goes out of one side of the cell, it will reappear back in again on the other side. And this is a way of modeling a macroscopic piece of material with finite computational resources. If you've done any solid state physics, then you should recognize the ideas here as pertaining also to Bloch's theorem, which is a way that we can solve the electronic structure of a system, an electron in a periodic potential. But I'm not going to go into the detail there. So atomistic simulations, as I said, we start with this big red box at the top right here, the energy. And from the energy, we can calculate all manner of things. We can calculate the cohesive energy of a molecule or a material. We can look at the elastic constants and the elastic properties of material. We can calculate the forces on the atoms. From the forces on the atoms, we can derive the structure of a material in its ground state. We can follow the trajectory that atoms take over time by using the forces, and that gives us dynamics. From dynamics, we end up with free energies, and that gives us all of the power of statistical mechanics and thermodynamics. And so there are all sorts of extraordinary things that we can calculate, and these are all used in different areas. Somebody I worked with for a long time, one of his most famous pieces of work was when he calculated using electronic structure, so quantum mechanics and atomistic simulations, he calculated the viscosity of liquid iron at the Earth's core. And until they'd done these calculations, the various experimental measurements that had been made covered about 14 orders of magnitude. So from, let's say, 1 up to 10 to the 14. This is because those experiments are rather difficult to do. We can't actually get down to the Earth's core. And by doing these calculations, he was able to bring it down to a factor of 2. So that was an extraordinary change in our knowledge of the Earth's core and its properties. So that's just one example of the kinds of things that we can do with this type of approach. Now, when we are going to do a simulation, we have to ask ourselves the question, how many atoms do we use? And if we're doing a perfect crystal, something like silicon, then if you've done any kind of solid state or condensed matter physics, you'll know that you can actually model the structure of silicon just with 2 atoms repeated. But if you're interested in real systems, so systems, say for instance in silicon, we use it for to make transistors, to make computers, which we're all using to watch this presentation. And in order to make it a functional material, we have to dope it. We have to introduce electrons to that material in order to allow it to conduct electricity. And when we're doping, a realistic doping level that you would find in a transistor would be somewhere around 1 dopant atom, so we use phosphorus typically as a dopant, to 100,000 silicon atoms. So to correctly model doped silicon in a transistor, we would need at least 100,000 atoms. That, however, is going to be more expensive than doing a smaller calculation. So we have to ask ourselves the question, how small can we go? What errors will we introduce? And so we have this tension that I've represented here between the efficiency of the calculation, the speed, if you like, and the accuracy of the calculation. So typically efficiency is going to involve few atoms. Accuracy is going to involve many atoms, and then we're also transitioning between the representation of a system, so stripping away some of the reality and a realistic description. And when you think about alloys, where the concentration of materials can be quite low, or doping, then you need to think about larger systems. If you have perfect crystals, you can have smaller systems. If you have defects and dislocations and surfaces, then you need a larger system. So I hope what you're starting to pick up here is that there's actually a key question, which is how can we do large systems efficiently? I'll come to that in a moment. Now, the first question we have to ask ourselves is how do we calculate the energy? How do we calculate the properties of the system? And that all comes down to how the atoms interact. And that's where the interesting physics is. Now, chemically, physically, atoms bond together, and that involves electrons. We also know that what are called non-bonding interactions involve electrons. That's the kind of thing that you might describe as a van der Waals force or a dispersion force, the kind of thing that holds together layers of graphite. So really, if we're going to be accurate in describing the interactions between atoms, we're going to need to do quantum mechanics. However, quantum mechanics is difficult and expensive computationally, so frequently people actually replace the quantum mechanics with a sort of an interaction like a spring. But those interactions, which are known as force field, are limited to the functional form that you can use. So they're complex, they're complicated, they're a lot faster than electronic structure calculations would be, but they're limited in their accuracy. And so we come now just to a brief overview of quantum mechanics. So these complicated interactions, these force fields as they're called, are successful. So for instance, in biochemistry, I don't know if you may have encountered things like charm or amber or approaches like VMD. In the materials world, they talk about lamps. All of these kinds of approaches use force fields, and they produce really good results for specific questions. But if you want to look at bond breaking, bond making, reactions, interfaces between materials you haven't been able to characterize, then you really need quantum mechanics. And typically in this area, quantum mechanics is divided into two areas. One is called quantum chemistry or post-Hartree-Fock or wave function methods, and the other one is called density functional theory. Both of these are approaches to solving the quantum mechanical problem, finding the electronic structure. In general, the scaling with size, i.e. with the number of atoms, is better for DFT. It's a little bit of a generalization, but it's largely true. Typically, standard DFT methods scale with the cube of the system size. So you double the system size, it becomes 8 times slower or 8 times longer to run. Quantum chemistry starts around about the 4th power. So again, you double the system size, it takes you 16 times as long. So just briefly, quantum mechanics is complicated. I've said that before. The Schrödinger equation that I've written down here, H psi is equal to E psi, that describes essentially any system that you want. We can write it down trivially, but we cannot solve it for anything. You can't solve it exactly for anything more complicated than hydrogen. Now, the first thing we do is just to separate out the nuclei, that's the atoms, away from the electrons because they're much more massive. We ignore their effects when we're solving for the quantum mechanics, but we still have the problem that electrons are many-body. And this is where the technique of density functional theory comes in. It's an exact reformulation of this many-body problem. We have independent electrons moving in an effective potential, but we then have to approximate that potential. I'm not going to give many more details than this. If you're interested in the physics, I'm very happy to discuss it further afterwards. But the point is that when we implement DFT, there are various different ways of doing it. The way that Conquest works is by using localized atom-centered functions to represent the wave functions. And what this means is that we can change the Schrödinger equation, this eigenvalue problem down at the bottom here, into a matrix problem. And we all know that there are extremely efficient ways of solving for the eigenvalues and eigenvectors of a matrix using linear algebra on large computers. And that's one of the techniques we use in Conquest. We will just diagonalize the matrix. This little H fellow down here, the Hamiltonian, can be written as a matrix. We can diagonalize it. That gives us the wave functions and the energies that we're interested in. And in Conquest at the moment, we use Scalapack to do that. That, of course, is n cubed. It scales with the cube of the matrix size, and the matrix is defined by the number of atoms in the system. However, Conquest also has an approach which is known as linear scaling, and this is where we use the fact that the matrices we've derived are sparse, and we do an optimization approach, and that means that we scale linearly with the system size. So if we double the system size, we double the computational time. If we have a computer 1,000 times more powerful, we can do 1,000 times more atoms, where with traditional diagonalization, you can only do 10 times more atoms. Again, if people are interested, I can give a little more detail. So this is just an overview of Conquest. It's from a few years ago when the K computer in Japan was still one of the largest in the world. And we've demonstrated that Conquest can be run on over 2 million atoms. We can get to the ground state there. And on the K computer, we've actually demonstrated perfect weak scaling to nearly 200,000 cores. We can do dynamics. We've shown that on about 32,000 atoms, and we've demonstrated real linear scaling applications. There are other codes in this area, which I've given down at the bottom there, that do linear scaling. But as far as sort of a line in the sand, we believe that Conquest is one of the leading codes in the world. So its capability is extremely efficient in its parallelization. So you can run it on a single core. I regularly run it on my laptop when I'm on the train, and that's where I've done a lot of the development, but you can also scale up to hundreds of thousands of cores. In terms of the number of atoms you can look at, it's scalable. So we go from 1 up to 2 million atoms, and it's completely open source. So we have an MIT license, and it's available on GitHub, and I think that you've been downloading it from GitHub. And this little graph at the bottom here demonstrates weak scaling. So that is where we keep the number of atoms per process, per MPI process, in this case per core, fixed, and increase the number of atoms. So therefore, as you go to larger numbers of atoms, you of course have to use larger numbers of cores. And you can see that here we're saying essentially perfect weak scaling, where the number of atoms goes up to 1 million here, and the number of cores down here on this purple line goes up to 200,000 cores. It does take a little bit of work to get performance, to get scaling quite this good. The strong scaling is not quite as good. That's not what we've optimized Conquest for. We've always intended it to be used for weak scaling. We also have a way of running it with the exact diagonalisation, which allows us to push the system sizes up towards several thousand or 10,000 atoms, which is larger than most codes can do. I just wanted to show you a couple of examples of the type of calculations that we do with the code. So this is a picture of a material, well, two materials. PTO is lead titanate, so lead titanium O3 oxide, sitting on STO, which is strontium titanate. And what we're interested in here is a property called ferroelectricity. So most people are familiar with ferromagnetism. It's the kind of magnetism that keeps the things that you stick on fridges up. This is a similar property, but it's for an electrical property of the system, not a magnetic property. And what we're interested in here is, so the top part here, this light gray, is a layer of lead titanate, and then the darker gray at the bottom is a layer of strontium titanate. And the context here is that strontium titanate doesn't normally show any kind of polarization or ferroelectric response, whereas lead titanate does. And we're interested in what the lowest energy structure of these displacements, these dipole moments within the lead titanate are in the context of a film. So a lot of people do calculations and measurements on what are called multi-layers, where you would repeat like a sort of a sandwich layer of, or a pancake stack, if you like, of strontium titanate, lead titanate, strontium titanate, lead titanate. And what we're doing here is we're looking at what happens when you just have these finite films. So you could have all of these little arrows. The little arrows here represent a dipole moment, so they're like a little magnet, a bar magnet, but they're electrical. And they could all line up in one direction, but that actually comes with quite a large energy penalty. And so what you find is that actually it's much better for them to start arranging themselves in domains. And if you've ever played with magnets and iron filings, there's kind of classic pictures where you put a bar magnet and scatter iron filings on top of it, use these kind of loops, which you might actually recognize here in the patterns of these electrical dipoles. And what we were able to show is that for a thick enough film, so this top picture here is a film which has got 9 unit cells, 9 boxes of lead titanate, then we start to form what are called domains. So that you get these loops where the polarization, these little electrical dipoles are going round in circles, and then they alternate backwards and forwards, which means that the net polarization of the film is 0. And so you get these walls between the domains where the dipoles are all lined up, and you'll see that you've also polarized the substrate. Whereas for a thinner film of lead titanates, this is only 3 boxes of lead titanate, there isn't space to form these kind of these circles, and so we have a polar wave, so a little wave of alternating directions. And this is interesting and important because this type of ferroelectric material might be useful for future memory storage, for very compact memory storage. You can imagine that each of these sets of up or down arrows might represent a bit, a 0 or a 1. And by doing full DFT calculations on these, we've shown that you actually can derive some very interesting and rather complex structures and also look at the effect of the surface. We went on to look at the effect of what happens if there's actually a sort of a scratch in the surface, and we find that that can affect the location of the walls between these domains. There are lots of other areas that we've applied it to. I've got some pictures and a little bullet list here. So we've looked at nanowires, what are called core shell nanowires. So you have a core of silicon and then a shell of germanium. These are of potential interest as the channels of future transistors. On the right here, we have a sheet of graphene on top of a rhodium substrate. This down here on the bottom left is another complex oxide, yttrium gallium oxide, where we're looking at little topological defects. So again, we're looking at the polarization in the surface and the electronic states. And these on the bottom right, these gold nanoparticles are interesting for catalysis. And we can contrast the effect of gold on its own or gold on a substrate. And here we've got magnesium oxide. I should point out that all of these are from my Japanese colleagues. And an area that I've been interested in for a long time is germanium on silicon. So silicon is a standard substrate that's used in all transistors. And germanium is very similar to silicon. It's just one row below it in the periodic table. So it's a slightly larger atom. So there's a strain between the two. So if you grow germanium on silicon, then to start with, it grows fairly smoothly. But then once you go beyond about 3 or 4 layers, you start to see what we're seeing here in these images. So these images are what are called scanning tunneling microscope images. And this is a rather large scale image. You can see that you're starting to get these large structures that are then shown in more detail on the right. They're known as hut clusters because they look quite like the roof of a house seen from above. They're 3-dimensional, they relieve the strain. And there's been some question for some time as to whether these kinds of structures could be used as quantum dots in various areas. And so we've actually done some modeling of these in Conquest. So these are getting to be quite large systems. So this is the largest hut cluster that we've modeled, where you can see these are about 30 by 40 nanometers. There's a couple of 100,000 atoms in this material. And we can look at, for instance, how these structures grow. So what you're seeing here in this image, these little yellow dots on top of the blue are showing how the next layer of one of these faces would attach, and we can calculate the energy of atoms at different places on these faces and understand how those faces grow and how these structures form, and therefore potentially how we can control it better. And this is it's a little bit complicated and difficult to see, but what it's showing you is, again, one of these hut clusters. That's the gray and the blue. But these red dots, these red blobs, are showing a plot of the wave function near the Fermi level. So the very top of the electronic structure that we've calculated using Conquest. And we see that it's largely confined to this hut cluster, and in fact at the surface of the hut cluster. So that tells us something about whether or not we'll be able to use it as a quantum dot. Just to let you know what we're wanting to do with Conquest in the future, we've got a current project which is working on multi-threading the code. And there are little bits of multi-threading in the code. In the instructions, you were told to use version 1.2, I think, for this task. We have actually released in the last couple of weeks version 1.3, which has more multi-threading but no GPU capability. But we want to start looking at how we can use a GPU implementation. This is, I think, vital for all HPC codes because all exascale machines are based on some kind of GPU or accelerator. We're going to be extending the functionality of the code. If you work in the area of electronic structure or physics, we're looking at adding in exact exchange. The linear scaling solving, which I've shown you bits of, is still a little bit restricted, sometimes not as efficient as we'd want it to be. So we want to improve that. And we want to think about other ways of representing the matrices, more efficient ways to shrink the sizes of the matrices. So just to finish, Ophir asked me to talk about the task overview for this competition. And what you're going to be doing is testing the scaling of this order n solver. So I showed you those graphs showing that excellent weak scaling is possible. You can also test good strong scaling. In both of these cases, it's quite important not to try and use too many processes. Conquest is limited by the number of, it has to have a finite number of atoms per process, that is MPI process. And if you push it too far, then it will fail. You can try OpenMP threading. You're welcome to experiment with that. And what I would suggest is maintaining the number of MPI processes multiplied by the number of threads. So if you have 10 MPI processes in one thread, you can try changing that to 5 MPI processes and 2 threads, or 2 MPI processes and 5 threads, etc., etc. It's perfectly possible to look at strong scaling. That will be limited by memory and numbers of atoms. So you can, obviously there's a minimum of about 8 atoms per MPI process. That's at the high end of number of processes. The amount of physical memory available to you on your system will determine how many processes you can go to. And in this first virtual part of the task, you're looking at weak, or if you like, also strong scaling for bulk silicon. The interesting question is the time per MPI process and the effects of the different parameters in the input file on the scaling. So we have actually provided 3 different input files, I think with 512 atoms, 1,728 and 4,096. So that's essentially allowing you to increase the number of processes by a factor of 8 as you go between those 3. So that'll allow you to look at weak scaling. You could also just choose one of those and try changing the number of processes to experiment with the strong scaling. And also you can experiment with the effect of OpenMP threading. Like I said, there is more OpenMP available in version 1.3 if you wanted to try that. That's about everything I think I wanted to cover. So I'll stop sharing my screen for the moment. I'll be happy to take any questions or to move on to other parts of the discussion.
Thank you, David. Let's open the stage for questions. I know it was a lot about the physics. So
yeah, I'm sorry about that.
No, it's okay. I hope the students learn about that and about how today's scientists are using the HPC applications to solve real life problems or to experiment and to enlarge the science knowledge.
Absolutely.
This is very nice. And yeah. So if you have any questions, just feel free to ask. If not, that's also okay. I know it was a lot. And we also have the Slack channel. I assume everyone here are in the Slack channel. Once you start experimenting with the application, if you encounter any issues, let us know. If any questions, let us know. We'll try to address that. We had a few questions. Yeah.
Sorry, I was going to say I should point out that if you're interested, if you look at the major HPC centers around the world, you'll find that DFT codes like Conquest or often something like VASP will use up to 1/3 of every HPC machine. This kind of approach is incredibly common on large machines and large centers. Yeah, did people have questions either in the chat or from
there was
Slack?
Some questions on the chat. I'll send it to you later, but they're asking about changing the inputs. And what we need to discuss it in general, but what we don't allow to change the inputs.
Okay.
Just because it may make the problem smaller. I don't know what they're doing. But for experiment, I don't mind if they want to experiment with that.
Sure.
For me, but eventually for submission, I'll just tell you that we will create a shared folder in OneDrive, and I'll send each team the folder, and you'll need to submit the results. And around the beginning of May, I need to check the exact agenda, but we will each team will have a presentation. You need to send us a PowerPoint, and you'll have about 40-45 minutes, to discuss your work and what you did, what you learned, and so on. So you need also to prepare for that. What might say, don't stuck. If you're stuck with something, just let us know. We'll try to help you. If you can't compile, if something happens, let us know. We are here for to help you, and hopefully you will enjoy it. You will take the benefits from participating in this a competition to your future life and future career. And maybe you will work with David. Who knows, right?
Yeah, I'd be very happy.
Yeah.
Very happy.
Okay. So again, last chance for questions. If not, it's totally fine. I understand that it's just the beginning and people are, just beginning experimenting. So any questions that you have, just the best thing would be to just put it on the Slack. I check it every day. And me, David Bowler or David Chow that helps me will try to help you. You're supposed to test it on PSC cluster, Bridges 2, on the CPU nodes. They have 2,000 CPU ROM nodes with the HDR, InfiniBand HDR connectivity over there. And you can allocate up to 4 nodes. So we won't burn too much of the CPU resources. We are asking to limit that to up to 4 nodes. And again, what to say? Good luck to the teams, and thank you, David, for helping us here. And yeah, here I see someone is trying to ask something. Go ahead.
Yes, so maybe I missed that, but so for now in the instructions, we just build the application and with the Conquest script, run some input simulation on the input data. Could you maybe specify what type of simulation is exactly running so that just have a high level picture of
Sure.
What is happening from your presentation?
Yeah, so what you're doing with the calculation is you're calculating a sample of bulk silicon. It's kind of a classical, it's a canonical kind of test that we would use, and the calculation you're doing is essentially calculating the total energy. So you're finding what's called the ground state, and from there you would then be able to do some kind of calculation where you moved the atoms around, or you tried to find the lattice constant of the material. But this sort of approach, finding the ground state, is the absolute center and core of all DFT calculations. So that's the bit that we're most interested in. I think it's probably the simplest single example you can do. So you're basically taking a large structure and you're finding the total energy for the system.
Okay, and you also said that we can try out OpenMP threading, right?
Yes.
Does it mean that you can modify the code, or
no? So I wouldn't recommend that. I mean, you're welcome to look at the code, but it's not trivial to understand. But so OpenMP is already implemented. So you would have to compile it with an appropriate flag, and then you'd have to set OMP num threads and experiment with the effect of that. The other thing that you might want to watch out for is if you do try OpenMP threading, there's a system parameter OMP stack size, which is sometimes set quite low to something like 2 or 3 megabytes. You might want to, if you have an unexpected crash, you might just try increasing that to sort of to 50 or 100 megabytes.
Okay, thank you. So like for now in the online part, we're basically dealing with the black box and testing it for scalability and strong scalability. Okay, thank you.
Okay. Anyone wants to ask anything else? Any other comments? Okay, so with that, I would like to thank David.
Yeah. Oh, sorry. There's a quick question. So
there's a question.
I mean, the stack size would be around. I would suggest sort of, you might need to experiment, but I would suggest 50 to 100 megabytes. Yeah. So it's a system variable, OMP underscore stack size. It's just an environment variable.
It's like that. I wrote it OMP underscore stack size.
Yeah, but because it's an environment variable, it needs to be in capitals. But yeah.
Capital.
Yeah.
Capital. Okay.
Okay.
Thank you so much, David. And again,
pleasure.
any questions, let us know if you're stuck, if something doesn't work. If you have any concerns, let us know. We'll try to help. And enjoy the process. Try to learn from it, and hopefully take it with you to your career. And we will have, I will send you later on the team folder, and I will per team I will set you time for a presentation. It will be after the end, so around the beginning of May. And we'll announce the results finally in Hamburg in the ISC event, and we'll of course send you on over Slack and let you know if you can't come. Okay, so thank you everyone, and we will have the next session in the next hour. So mine is 9 a.m. So you have about 20 minutes, take a coffee and come back with the next link. Okay.
Bye-bye, From.
Thank you, everyone. Bye-bye.